Okay, so just a reminder, a series is just a sum of the terms in an infinite sequence. The thing we want to make sure that we keep straight is we can also view a series as a sequence itself, namely the sequence of partial sums. So the sum of a series will be equal to the limit as n approaches infinity of the sequence of partial sums where, so remember that sequence is the first term would just be the same as the first term in the associated sequence. It would be A1, right? But the second term in this series, or in this sequence, would be A1 plus A2. And then the third term would be A1 plus A2 plus A3, and so on, right? All right. I forget where we got. So we say the series is convergent if the sum adds up to something finite, and it's divergent otherwise. We developed a formula for the sum of a geometric series, and it's going to converge if the constant multiple is between negative and positive 1. We did a couple examples of that. We showed that the harmonic series must be divergent. Okay, so I think this is where we stopped, right? So here's our theorem. And the theorem is that if the series is convergent, then the corresponding sequence must converge to 0. All right, and what to kind of put this in layman's terms, all this means is that the terms must get smaller, right? Now, the converse of this isn't necessarily true, meaning just because the limit of an goes to 0 doesn't mean that the series has to converge. And we saw that with the harmonic series, right? Like these terms are getting smaller. 1/2, 1/3, 1/4, and so on. Those are getting smaller, but we proved that this is divergent. Okay? So if the series converges, then the corresponding sequence will go to 0. But just because the corresponding sequence goes to 0 doesn't necessarily mean that the series has to converge. So that's in logic, you can say that's necessary but not sufficient. It's necessary that they go to 0, but just because they go to 0 doesn't mean the sum will converge. All right, so let's prove this bad boy. All right, so I'm going to let Sn equal A1 plus A2 and so on up to An, right? All right, so Sn minus 1 would then be A1 plus A2 and so on, but it would only go up to An minus 1, right? So then if I take Sn and I subtract Sn minus 1, what's that going to leave me with? Just An, right? Good. All right, so what we're assuming is that this is true. The hypothesis is true. So assume this. So we're assuming sigma an is convergent. So I can say since sigma an converges, then the sequence Sn also has to converge by definition, right? Because they'll converge to the same thing. So the sequence of partial sums will converge to the overall sum sigma an, right? All right, so then let's let let the limit as n approaches infinity of s sub n equal s. So we're just saying it converges to some sum s, right? Well, it's true that n minus 1 will approach infinity as n goes to infinity, right? You guys agree with that? So if we let n go to infinity, then n minus 1 is still going to go to infinity. So the limit as n approaches infinity of s sub n minus 1 also has to equal s. In which case, I'm going to move up because I'm bad at organizing my space. In which case, the limit as n approaches infinity of an, which we already said an equals s sub n minus s sub n minus 1, right? Tommy told us that over here. Well, what is that going to equal? What did we say that s sub n will equal as n approaches infinity? This one? That's just s, right? And what does s sub n minus 1 go to? Also s, which is 0. So we've proven that if a series converges, its corresponding sequence will go to 0. Okay, so from that, we get what's called the test for divergence. So the converse isn't necessarily true. As I said, we can't just flip the conclusion and the hypothesis and have it be true. It's not true necessarily that if the limit of an is 0, the series is convergent. But this is called a conditional statement. You guys remember dealing with these in geometry, if-then statements? So the converse isn't necessarily true, but the contrapositive is going to be logically equivalent to the original statement. The contrapositive is when you flip hypothesis and conclusion and negate both of them. So in this case, it is true that if the limit of an is not 0, then the series will not be convergent, aka it will be divergent. Does that make sense? And that's what the test for divergence says. If the limit as n approaches infinity of an does not exist or is not 0, then the series associated sigma an is divergent. So this one does have a name, which just means that you'll be expected to cite it when you use it. All right, let's do an example. We're going to show that this series diverges. So I'm going to look at the associated sequence an, which is just n squared over 5n squared plus 4. I'm going to take that sequence, I'm going to divide the numerator and the denominator by n squared in this case. So that's just going to give me 1 over 5 plus 4 over n squared. And then I'm going to take the limit as n approaches infinity of that. So all the constants stay constant, but what does 4 over n squared do as n approaches infinity? So that term, what does that do as we let n get infinitely large? That goes to 0, right? So the whole thing will go to 1 over 5 plus 0, or 1/5, which is definitely not 0. So I'll say, therefore, sigma an diverges by the test for divergence. So hopefully that makes sense, that the terms would have to get infinitely small for the series to add up to something. In this case, the terms just go to 1/5. So you're just going to be adding terms that are not getting close to 0, they're just getting close to 1/5. Well, even if you just add 1/5 to itself infinitely many times, that's going to diverge. That's going to add up to infinity, right? All right, I think we got a couple of properties. So hopefully these are intuitive, because a series is just a sum. So if you have a constant multiple, so if you have c times an, then that means c is just going to be in every term of the sum. So you can factor c out of the entire sum, aka you can factor c out front of the sigma, right? And then if you have a series of a sum of two sequences, you can just deal with them separately. So you can look at them as sigma an plus sigma bn. That's just because addition is associative. And same idea with subtraction. So if I have sigma an minus bn, I can deal with it as sigma an minus sigma bn. Okay. So last example. So if I'm taking sigma of 3 over n times n plus 1 over 2 to the n, and I want to find the sum, I can use those properties. So the first thing I'll do is just split those up. into 2 sigma, so I'll have sigma 3 over n times n plus 1 plus sigma 1 over 2 to the n. All right, and that first sigma, I have a constant multiple. I have that 3, so I can factor that out. So 3 sigma 1 over n times n plus 1 plus, now this second one is actually geometric. Remember that our general formula for a geometric series is sigma a times r to the n minus 1, right? So if I take out a factor of 1/2, then what I'm left over with is 1/2 to the n minus 1, right? And now that looks like a geometric series. Okay.
I know we did that yesterday.
Yes.
But the n minus 1
Remind you why?
Yeah.
So just think about it. This is a product of powers. This is technically 1/2 to the 1, right? So you would add the exponents, right? So that would be 1/2 to the 1 plus n minus 1, right? Which is just 1/2 to the n. Now 1 to the n is always just going to be 1, so that's the same as 1 over 2 to the n. Does that make sense? Yeah. This over here, 1/2 times 1/2 to the n minus 1. Because product of powers, so if I have a to the m times a to the n, the base doesn't change, you just add the exponents. All right. All right, so I have 1/2 times 1 over 2 to the n minus 1. Great. This is an example that we already proved yesterday. This was that telescoping series. So if you flip back to your, what was it, example 2, we actually already evaluated that series and we found its sum and it added up to 1, right? Great. So what we have here is then 3 times 1 plus, this is geometric, so we can just find its sum using the geometric sum formula, which is a, in this case a is 1/2, over 1 minus r, in this case r is 1/2, this is 1/2 over 1/2, which is just 1, right? So we have 3 times 1 plus 1, and our answer is 4. So there you go. This series converges to 4. All right, and that is that. So we got a good chunk of time that you can work on both the problem set and the group work. The group work is just 2 problems. I think there should be a PDF of it up there for you.
Thank you.
So you got to know a little geometry for these. So like area of a circle is pi r squared, right? So area of half a circle is pi r squared over 2. So my suggestion is find the first few shaded areas, and you're going to be adding those together, right? And then look at the terms and figure out if there's a way you can get from one term to the next to create a more general formula for the series.